Potential problems exist when using a step-down transformer as a step-up transformer. Firstly, shorted windings can occur. Step-down transformers are designed to handle lower voltages and higher currents. When used in reverse, the windings can become overloaded and short out. Secondly, overheating is a concern. The transformer may overheat due to the increased voltage and reduced current flow. Thirdly, reduced efficiency will happen. The transformer's efficiency will be reduced, consuming more power and potentially tripping the electrical system. Fourthly, safety hazards are present. Overheated transformers can pose a fire risk or cause electrical shocks. Fifthly, voltage regulation issues can arise. Step-down transformers are designed to regulate voltage by reducing it. Using them in reverse can compromise voltage stability. Sixthly, the warranty might be voided. The manufacturer's warranty may be voided if the transformer is used in a manner not intended. Additional concerns include the following. 1. There is no underwriter's laboratories listing. Step-down transformers are typically not underwriters' laboratories listed for use as step-up transformers, which can raise safety concerns. 2. There is limited capacity. The transformer may not have the capacity to handle the higher voltage and reduce current requirements of the equipment. 3. Physical damage can occur. The transformer's construction and terminals may not be suitable for the increased voltage and reduced current flow. It is strongly recommended to avoid using a step-down transformer as a step-up transformer. Instead, use a properly rated step-up transformer designed for the specific voltage requirements of the equipment. Transformers are essential components in electrical power systems, enabling efficient voltage transformation to meet diverse application needs. Understanding the construction, operation, and proper application is crucial for ensuring safety, reliability, and optimal performance. A transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. It typically consists of two or more coils of wire, called windings, which are electrically isolated but magnetically linked. The primary winding receives energy from the source, and the secondary winding delivers energy to the load. The core, usually made of laminated iron or steel, provides a path for the magnetic flux, enhancing the coupling between the windings. The operation of a transformer is based on Faraday's law of electromagnetic induction. When an alternating current flows through the primary winding, it creates a time-varying magnetic flux in the core. This flux induces a voltage in the secondary winding proportional to the turns ratio between the primary and secondary windings. The turns ratio, denoted as N, is the ratio of the number of turns in the secondary winding, Ns, to the number of turns in the primary winding, Np. That is, N equals Ns divided by Np. If N is greater than 1, the transformer is a step-up transformer, increasing the voltage from the primary to the secondary. If N is less than 1, the transformer is a step-down transformer, decreasing the voltage. The voltage and current relationships in an ideal transformer are governed by the following equations. Vp divided by Vs equals Np divided by Ns, and Ip divided by S equals Ns divided by Np, where Vp and Vs are the primary and secondary voltages, respectively, and Ip and Is are the primary and secondary currents, respectively. In a real transformer, losses occur due to various factors, including the resistance of the windings, hysteresis and eddy current losses in the core, and stray fluxes. These losses reduce the transformer's efficiency, which is defined as the ratio of the output power to the input power. Transformer efficiency is typically very high, often exceeding 95% for large power transformers. Transformers are classified based on various criteria, including their construction, application, and voltage level. Based on construction, transformers can be classified as core type or shell type. In a core type transformer, the windings surround the core, while in a shell type transformer, the core surrounds the windings. Based on application, transformers can be classified as power transformers, distribution transformers, instrument transformers, and isolation transformers. Power transformers are used in high voltage transmission systems to step up or step down voltage levels. Distribution transformers are used in local distribution networks to provide voltage levels suitable for residential and commercial customers. Instrument transformers are used to measure high voltages and currents accurately and safely. Isolation transformers are used to isolate electrical circuits, providing safety and reducing noise. Based on voltage level, transformers can be classified as low voltage, medium voltage, or high voltage transformers. Low voltage transformers typically operate at voltages below 600 volts. Medium voltage transformers operate at voltages between 600 volts and 69 kilovolts, and high voltage transformers operate at voltages above 69 kilovolts. Proper transformer selection and application are crucial for ensuring safe and reliable operation. Factors to consider when selecting a transformer include the voltage and current ratings, the kVA rating, the insulation level, the cooling method, and the environmental conditions. The voltage and current ratings must be matched to the application requirements to avoid overloading or underutilizing the transformer. The kVA rating determines the transformer's capacity to deliver power. The insulation level must be adequate to withstand the operating voltage and any transient voltages. The cooling method, such as air cooling or oil cooling, must be appropriate for the transformer's size and operating conditions. The environmental conditions, such as temperature, humidity, and altitude, must be considered to ensure proper transformer operation and longevity. Transformers require regular maintenance to ensure their continued safe and reliable operation. Maintenance tasks include inspecting the transformer for signs of damage or deterioration, testing the insulation resistance, checking the oil level and condition, and tightening connections. Regular maintenance can help prevent failures and extend the transformer's lifespan. The National Electrical Code, or NEC, provides guidelines for the safe installation and operation of transformers. Article 450 of the NEC covers transformers, including requirements for overcurrent protection, grounding, and ventilation. Adhering to the NEC requirements is essential for ensuring electrical safety and preventing fires or other hazards. In summary, transformers are essential components in electrical power systems, enabling efficient voltage transformation. Understanding their construction, operation, classification, selection, application, maintenance, and the applicable NEC requirements is crucial for ensuring safety, reliability, and optimal performance. When dealing with electrical systems, it is imperative to consult with qualified professionals and adhere to all applicable codes and standards. Ignoring these guidelines can lead to serious consequences, including equipment damage, personal injury, and even death. Furthermore, always exercise caution and use appropriate personal protective equipment, or PPE, when working with electrical equipment. Remember, safety should always be the top priority when dealing with electricity. Let's delve into more detail about the potential problems of using a step-down transformer in reverse as a step-up transformer. As previously mentioned, one significant concern is the potential for shorted windings. Transformers are designed with specific voltage and current ratings for their primary and secondary windings. A step-down transformer is engineered to handle a higher voltage on its primary side and a low voltage with a correspondingly high current on its secondary side. When you reverse the connections, you are now applying a lower voltage to what was originally the secondary winding. This winding is not designed to withstand the higher voltage that will be induced on the original primary winding, now acting as a secondary. The insulation between the windings may break down, leading to a short circuit. The insulation material used in transformers is carefully chosen to withstand specific voltage levels. Exceeding these levels can cause dielectric breakdown, resulting in a short. The consequences of shorted windings can be severe, including transformer failure, power outages, and potential fire hazards. Overheating is another major concern. When a step-down transformer is used in reverse, it may not be able to dissipate heat effectively. The core and windings are designed to operate within a specific temperature range. Exceeding this range can cause the insulation to degrade, leading to premature failure. The cooling mechanisms, such as oil immersion or air cooling, are designed based on the expected heat generation under normal operating conditions. When the transformer is used in reverse, the heat distribution and dissipation characteristics change, potentially leading to localized hot spots and overall overheating. Overheating can also cause the transformer oil, if present, to degrade more rapidly, reducing its insulating properties and further exacerbating the problem. Reduced efficiency is also expected when a step-down transformer is used in reverse. Transformers are designed to operate at maximum efficiency within a specific voltage and current range. When these parameters are significantly altered, the transformer's losses increase. These losses include core losses, such as hysteresis and eddy current losses, and copper losses in the windings. Using a step-down transformer in reverse can lead to increased core saturation, resulting in higher core losses. Additionally, the increased current in the windings can lead to higher copper losses, further reducing efficiency. The reduced efficiency not only wastes energy but also contributes to increased heat generation, compounding the overheating problem. Safety hazards are a significant concern when using a step-down transformer in reverse. The potential for overheating, short circuits, and insulation breakdown can create dangerous conditions. Overheated transformers can pose a fire risk, especially if they are located in enclosed spaces or near flammable materials. Short circuits can cause electrical arcs, which can ignite nearby materials. Additionally, insulation breakdown can expose conductive parts, creating a risk of electrical shock. It is crucial to ensure that all transformers are properly grounded and protected by appropriate overcurrent devices to minimize these risks. Voltage regulation issues can also arise when using a step-down transformer in reverse. Transformers are designed to maintain a relatively stable output voltage under varying load conditions. A step-down transformer is optimized for voltage regulation when stepping down voltage. When used in reverse, its ability to regulate voltage may be compromised. This can lead to voltage fluctuations on the secondary side, which can negatively affect the performance of connected equipment. Sensitive electronic devices are particularly susceptible to voltage fluctuations, which can cause them to malfunction or fail prematurely. Voiding the manufacturer's warranty is another potential consequence of using a step-down transformer in reverse. Transformer manufacturers typically specify the intended use of their products, including the voltage and current ratings and the direction of power flow. Using a transformer in a manner not intended can void the warranty, leaving you responsible for any repairs or replacements. Before using a transformer in a non-standard application, it is essential to consult with the manufacturer to determine if it is suitable and to ensure that it will not void the warranty. The absence of an underwriter's laboratories listing for reverse use is another important consideration. Underwriters Laboratories is a recognized testing laboratory that evaluates products for safety. Transformers that are intended for use in specific applications, such as step-up or step-down, are typically tested and listed by Underwriters Laboratories to ensure that they meet safety standards. Step-down transformers are typically not Underwriters Laboratories listed for use as step-up transformers. Using an unlisted transformer in an application for which it is not designed can raise safety concerns and may violate local electrical codes. Limited capacity can also be a problem. Step-down transformers are designed to handle specific voltage and current levels. When used in reverse, they may not have the capacity to handle the higher voltage and reduced current requirements of the equipment they are powering. This can lead to overloading, overheating, and premature failure. It is essential to carefully consider the voltage, current, and kV amps requirements of the equipment and to select a transformer that is adequately rated for the application. Physical damage is another potential concern. The construction and terminals of a step-down transformer may not be suitable for the increased voltage and reduced current flow when used in reverse. The terminals may not be rated for the higher voltage, and the physical stresses and the windings and core may exceed their design limits. This can lead to physical damage, such as cracked insulation, loose connections, and deformed windings. Such damage can compromise the transformer's performance and safety. In light of these potential problems, it is strongly recommended to avoid using a step-down transformer as a step-up transformer. Instead, use a properly rated step-up transformer designed for the specific voltage requirements of the equipment. A step-up transformer is specifically designed to handle the higher voltage and reduced current flow, and it will provide better performance, safety, and reliability. When selecting a step-up transformer, it is essential to consider the voltage, current, and kVA requirements of the equipment, as well as the environmental conditions and any applicable codes and standards. Consulting with a qualified electrical engineer or transformer manufacturer can help ensure that you select the right transformer for the application. Additionally, regular inspection and maintenance are crucial for ensuring the continued safe and reliable operation of transformers. This includes checking for signs of damage or deterioration, testing the installation resistance, and verifying the proper operation of protective devices. In summary, while it may be tempting to use a step-down transformer in reverse as a step-up transformer, the potential problems and risks outweigh the benefits. Using a properly rated step-up transformer is the safest and most reliable option for meeting your voltage requirements. Always prioritize safety and consult with qualified professionals when working with electrical equipment. Remember that electrical systems can be dangerous, and it is essential to follow all applicable codes and standards to protect yourself and others.